So Joey Schulz is an aerothermodynamicist working at NASA Ames Research Center and is currently the lead developer of the Icarus material response solver. In addition to working on the computational modeling of material response, he also aids in the development and maintenance of NASA Ames CFD and radiative transport simulation software. So with that, go ahead and take it away, Joseph.
All right, can everybody see my screen?
Yes, I think so.
Excellent. All right, thank you very much. So thanks for everyone's attention today. I will be speaking about a series of material response simulations using the code Icarus to conduct a Monte Carlo analysis of the in-depth temperature response of the Dragonfly aeroshell. So why are we interested in this? The instrumentation suite that will be embedded into the Dragonfly aeroshell will be the first ever dataset of its kind of the Titan environment. And while I don't have time to give a complete overview of the Dragonfly Entry Aerosciences Measurements or DREAM suite, there are many detailed presentations and publications that are publicly available, in particular, a recent IPPW talk in 2022, just last week. So in short, the DREAM suite is very similar to the Medley and Medley 2 instrumentation suites used for MSL and Mars 2020, and will contain radiometers, pressure transducers, heat flux sensors on the aft body and on the forebody. And of particular relevance to this particular study here, thermocouples. As with the Medley and Medley 2 instrumentation, these thermocouples are embedded inside a plug, which we refer to as the Dragonfly Sensors for Thermal Reconstruction, or dragster plugs. A picture shown on the right here. These dragster plugs will nominally contain 1 to 3 thermocouples per plug at different depths and orientated across the aeroshell and the backshell. The design of this is still in determination, but for as reference, the Medley 2 instrumentation suite used 2 types of thermocouples, an R-type thermocouple, which was used for all near-surface TCs on the forebody, and K-type thermocouples, which were used further in depth on the forebody and on all backshell locations. So one of the primary science objectives of DREAM is to use these TC measurements for the determination of the location of the laminar to turbulent transition. However, in determining the design of the dragster plugs, we have 2 opposing criteria. Each TC type or thermocouple type has a maximum operation temperature limit, which a conservative design would dictate locating the TCs further in depth. However, it's known that near-surface TCs are more sensitive to the time-varying aerothermal environment, which is important in order to capture the laminar to turbulent transition. So therefore, to best accomplish the science mission, we want to locate the thermocouples as close as possible to the surface, but still maintain the integrity of the thermocouple itself. So in order to accomplish this and to design the dragster plugs correctly, we need to account for the inherent uncertainty in the problem. And we do this by conducting a Monte Carlo analysis using a material response simulation. In particular, we'll use Icarus here. And we'll consider 2 different types or sources of uncertainty. The first source of uncertainty comes from the aerothermal environment itself, and these manifest themselves as boundary conditions to the simulation. And the second is just the inherent uncertainty in the TPS properties or the material properties itself. And these manifest themselves as different in-depth temperature responses. And while I'll give a more detailed discussion of how the Monte Carlo analysis was constructed and the design of experiments of this approach, I first want to give a quick overview of Icarus, and in particular, its relevance to this particular problem. So the primary motivation of developing Icarus was to retain the heritage one-dimensional analysis tools that we have traditionally supported with FIAT in our branch at NASA Ames, such as TPS sizing, which is shown here on the left, and uncertainty quantification. And we want to be able to extend this analysis to more complex 3-dimensional aeroshells, such as this Icarus simulation of the adept heat shield shown here. The governing equations of Icarus are very similar to other engineering material response codes and consist of the following set of governing equations. Up top, we see a set of kinetic equations of Arrhenius form that control the decomposition of the material, where in here is the total number of material components. The initial state of the material is referred to as virgin, and as the material undergoes decomposition, it approaches a final state which we refer to as char. The material properties are linearly varied between the virgin and char states. For example, the enthalpy of the material is some linear interpolation of the virgin mass fraction. Because many TPS materials that are relevant to reentry problems produce gaseous products during decomposition, we must account for the production and transport of pyrolysis gases on the in-depth temperature response. And so to do that, we include an additional set of conservation equations for the transport and production of pyrolysis gases, which we assume are in local thermal equilibrium with the material. And in particular, we take a simplifying assumption, in this case, to remove the momentum equation and use Darcy's law to determine the velocity of the gas as a linear proportional constant to the pressure gradient. Lastly, it's important to note that many material properties have some orientation dependence, meaning that the thermal conductivity and the permeability are not necessarily scalars, but are orthotropic properties, or in other words, rank 2 tensors. So before applying Icarus to the current problem, we need to perform a series of verification test cases. So I want to briefly describe this to not only show that Icarus is capable of analyzing such a problem, but also some of its relevance to the Dragonfly problem that we're discussing today. So within the material response community, a set of verification test cases have been devised to better understand how different assumptions within our material response code affect our results. And this set of test cases is referred to as the ablation workshop test cases, 2 of which are presented here. And in particular, we are doing a code-to-code comparison between Icarus and 2 well-known and well-established material response codes, Fiat on the left and Pato on the right. And the figures that you see below are time history of the temperature at different in-depth locations. And this approach effectively simulates a thermocouple measurement. And so we'll be seeing these types of approaches further in the results. On the ablation test case 1, we have a very simple single material that's non-ablating with a time-varying isothermal boundary condition. And we see that the comparison to Fiat results in a root mean square error of less than 7 degrees Kelvin. We can increase the complexity of the physics that we're modeling by including ablation and also including a more sophisticated boundary condition where we solve for the state of the surface, the temperature and pressure state of the surface using a surface energy balance, which is described here, where I have generalized this form to lump all of the surface effects, ablation, pyrolysis gas blowing, etc., into this QS term here, which we'll see later in the application to Dragonfly. And this just incorporates the effects of radiation and re-radiation and the in-depth conduction of the surface. We also need to verify that Icarus can handle a realistic TPS geometry. For instance, it needs to be able to include multiple materials, which can be either pyrolyzing or non-pyrolyzing, orthotropic or isotropic. And it also needs to be able to handle the material orientation. So in this contrived verification test, we have a cylindrical domain that's constructed of 2 materials, a orthotropic pyrolyzing material on the outer, and on the inner layer, we have a non-porous material. So what we would expect qualitatively from this is that the gases produced during the decomposition are forced out through the surface and do not propagate into the inner non-porous material. And so to handle this, we have to numerically impose this interface boundary condition to prohibit this. And that's illustrated here. Secondly, we, in order to prove to ourselves and to illustrate the effect of the orthotropic nature of many of these materials, there are two ways in which we can input this into the simulation tool. One is by which imposing the orientation of the material to be normal to the surface vector, meaning that it's a conformal TPS material. And the other would be to prescribe some kind of Cartesian or rotation about some Cartesian axis. And this does have some effect on the in-depth temperature response at two different locations, which is illustrated above. Lastly, since the TPS material that is chosen for Dragonfly is Pika, we need to validate that our Pika material model is sufficient and accurate. And to do this, we leverage a exhaustive ArcJet campaign that was done in 2009 and validated for Fiat. And out of this large campaign, six cases were selected for detailed study. And we have repeated these cases in Icarus. And I'm going to highlight three cases here in particular to illustrate the verification of this material model. For the lowest heat flux considered, 107 watts per centimeter squared, the measured centerline recession was 2.33. Icarus is predicting approximately 2.22 millimeters of recession, and the in-depth temperature responses are reasonably matching well to Fiat examples. Increasing the heat flux to 246 and 744 watts per centimeter squared on the left and right respectively. We have Icarus in the solid line, Fiat in the dashed line, and the experimental results in the dots here. And overall, we see a very good agreement between of Icarus, Fiat, and the experimental data, which gives good confidence in our modeling predictive capability. So after this, we've kind of overviewed the verification. Now, how are we going to apply this to the Dragonfly problem? So to recall, we want to determine the optimum TC depth. And we want to do this by including the uncertainty in the aerothermal environment and the material properties of the Pika. And as a preliminary investigation, we are just going to focus only on the stagnation point and only consider a 1D material response simulation. In order to effectively do this analysis, we leverage two different Python tools that automate this process. The first is referred to as Icarus Pi, which is essentially a Python wrapper around Icarus that manages and automates the simulation and data reduction of the material response simulation. And secondly, another tool called UQ Driver, which is will be discussed in the following slides. And lastly, I want to mention that the maximum operating temperature of an R-type TC is assumed to be 750 Kelvin, and the maximum temperature for a K-type TC will be 1530 Kelvin. I will refer to R-type and K-type TCs later in the data analysis. So the uncertainties in the aerothermal environment are incorporated into the surface energy imbalance. And here is the surface energy imbalance that I showed earlier, where I have lumped the effects of pyrolysis gas blowing into this QS term. There will be no ablating terms because Titan is a non-oxidizing environment. And this QS term here will come from a CFD calculation. The radiative heat comes from a radiative transport calculation, which are provided as nominal and margined environments for this trajectory. And so we assume that the uncertainty is bounded by the nominal as a lower bound and the margined as an upper bound. And the solid line here is the mean for both the convective heating, which in this case is QS, the radiative heating given by the yellow red line here, and the pressure, the green line, which is on the right axis. For the Pika properties, since we are just adopted from a previous study of the Medley 2 flight reconstruction, you can reference this AIAA paper here, and those distributions are provided below, where the char and virgin density have a uniform distribution, and the remaining material properties have some normal distribution, with the char thermal conductivity being correlated to the virgin thermal conductivity. Overall, this gives a total of 12 independent uncertain variables. And so to do our design of experiments and the subsequent statistical analysis, a tool called UQ Driver has been created. And this framework effectively allows for the managing of any type of general sensitivity analysis and uncertainty quantification by providing a flexible layer that allows you to hook into any choice of backends, such as Dakota or anything that you choose, really. It also allows for you to decouple the design of experiments to the actual running of the simulations, since many times we optimize the running of these through batching to supercomputers. It's also been noted that UQ Driver has been used to calculate the sensitivity analysis and the uncertainty quantification for inverse analysis, which will be used on the Artemis missions. So for this problem, the statistics have been collected using 500 samples, which have been selected using Latin hypercube sampling over the feature space of 12 independent uncertain variables. And we use a one-dimensional material stack-up, which predominantly consists of pica and aluminum honeycomb. The time step chosen for these simulations in order to simulate the full 372 seconds of the heat pulse is geometrically increased from a small value to 0.01 seconds. The mesh spacing is shown to be adequate and hyperbolically stretched using a minimum mesh spacing of 0.1 millimeters. In order to optimize the data collection, this process takes advantage of a ability within Icarus to customize the data files that are written out during the simulation. So at each time step, the maximum in-depth distance at which a temperature is above either the R-type or K-type limit is recorded, and that data is then reduced and shown in the following visualization. So this is a scatter plot of the distribution of the TC depth at which the temperature threshold is exceeded for both R-type and K-type. R-type is shown here and K-type is shown here, versus the time at the last time from entry at which that temperature is exceeded, which is on the vertical axis. This scatter plot is then reduced into a KDE distribution, and it's obvious that we are getting some sort of kind of multimodal effect, which is presumed to be effect of some discretization process in our simulation. Since we did account for the spatial discretization by linearly interpolating that distance, it was assumed that this was an artifact of the temporal discretization, which we were able to show was true by reducing the maximum time step that the simulation took. And if we do that, we recover a much more expected distribution and a more spread out scatter plot. It should be noted, however, that the mean values, the mean depths for both the R-type and K-type were the same in both simulations. Okay, to conclude, the Monte Carlo analysis found that the minimum TC depth for an R-type TC was 0.5 millimeters with a fairly small variance, and for the K-type TCs, a minimum depth of 2.1 millimeters. With respect to the Mars 2020 design, the R-type TCs were installed at 1.91 millimeters at the lowest, and this was largely due because ablation was expected at Mars, and therefore there was a lot more conservatism in the design, while only a minimum amount of ablation recession is expected in Titan due to the non-oxidizing environment. While these analysis was just done at the stagnation point, we are expected to, or we plan on repeating this analysis at other locations on the aeroshell, particularly at the shoulder, where we would expect some additional uncertainties due to the turbulent transition of the boundary layer at those locations, to affect this analysis. And with that, I'd like to thank the ESM project for funding, and of course the entire Icarus development team for supporting this work. And with that, I will take any questions.